So welcome everybody to the Rocky Mountain Mathematical Physics Seminar. Today we have a guest from the chemistry department at CU Boulder, Professor David Jonas, and he will speak about the geometry of nodes in non-adiabatic quantum mechanics. Thank you, David, for visiting us.
Okay. Thank you very much for the invitation. And this talk will be given at a fairly basic level. I didn't want to say elementary level because that usually means second or third year graduate text in mathematics from my experience with mathematics books. All right. And so the story I'm going to tell you about today has its origins in the work of one of my graduate students, Peter Foster. And so I'll kick into the slideshow. And hopefully that is working all right for everybody. And so, as I mentioned, this is about primarily from the thesis work of Peter Foster, who's now an assistant professor at Newbury College. And so in outline, what I'll start off is I'll start with a reminder of the adiabatic approximation, and then I'll explain a little bit about the photosynthetic mystery that got us into looking at a rather bizarre regime for non-adiabatic dynamics. And then what I'll do is I'll talk about non-adiabatic factorization. This part of the idea came from, in my group, work of my graduate student, Bill Peters, who preceded Peter Foster. And then I'll talk about the conical nodes that Peter Foster discovered and why we call them conical nodes. It turns out that these have an index, and the index is got connections to conical intersections and to Berry phase. And then I'll talk about the stability of this index. So the index is the thing that is most stable. And so as a reminder, the adiabatic approximation, in molecular quantum mechanics, we divide things up. The Hamiltonian can be split into an electronic part and a vibrational part. And the overall eigenstates are written here. They're a function of electronic coordinates and vibrational or nuclear coordinates. And you get, overall eigenfunctions. And the adiabatic approximation is to say, well, the light electrons are fast, the heavy nuclei are slow, and we're going to treat the vibrational coordinates as the slow parameter in the adiabatic theorem. And so if we do that, we fix the vibrational coordinates, solve the electronic Schrodinger equation at fixed vibrational coordinates to obtain electronic eigenvalues and electronic eigenfunctions, then use the set of electronic eigenvalues as a function of coordinates as a potential energy surface for the nuclei. And then we put that in and solve for the vibrational energy levels. And the adiabatic eigenfunction is a product of the electronic eigenfunction with its set of vibrational eigenfunctions. And what we left out is this pesky thing where the electronic Hamiltonian actually has an effect on the vibrational eigenfunctions. And so you're approximating that as zero. And in the sense of light electrons being fast, you're thinking about large energy gaps so that the Bohr frequencies are high. And then that should be just fine. That's the sort of going thinking, usually. And in your m-dimensional vibration, if you have an m-dimensional vibrational space, the adiabatic nodes will have dimension m-1. Nodal points in 1D, nodal curves in 2D, nodal surfaces in 3D. etc. So now we get to the photosynthesis problem and the mystery, okay? And photosynthesis is really more of a mystery to us rather than the plants, okay, right? But you see a lot of photosynthesis in this picture: trees, grass, and the pond scum down here, right, as well. And so it has provided all of our fossil fuels, and it provides all the oxygen we breathe. And it's actually quite an efficient process from a quantum point of view, okay? And it has to do something amazing to make a fuel. I mean, you're talking about harvesting something like 48 photons in order to make 1 molecule of sugar, all right, in the end. And the process involves typically thousands of chlorophylls acting as an antenna for a reaction center, all right, which is the place where the chemistry happens. So the thousands of chlorophylls, their job is just to absorb light and transfer that light to the reaction center where the energy can be used to do the chemistry. And when the reaction center was discovered by biologists back in the 30s, James Franck and Edward Teller tried to, figure out how this whole process worked using what was then a new theory of excitons, or delocalized excitations, that are, so molecules might share an excitation, and that could be used to transport energy. And their conclusion at the end of this paper is they thought that biologists are wrong, because every step involved would have to work perfectly, practically every time, and take place within a couple hundred femtoseconds, every single step. And they couldn't figure out how the steps could take place in a couple hundred femtoseconds. Well, the answer is the biologists were right. The steps are essentially perfect, and they all take place in a couple hundred femtoseconds. And the mystery has been, since that time, how does that happen? Okay, that's been the big mystery. And I'll tell you a little bit about the how. So the first thing to know is that the chlorophylls are not all just sitting there, okay? They are actually held in place in proteins. And there's a very rigid geometry, chlorophyll here, chlorophyll there, that sort of thing, that you can determine with structures by modern techniques. And because the pigments are bound to amino acids, the amino acids actually adjust the energies of the chlorophylls so that they're not all the same, so that there's a little bit of a downhill energy funnel in most of the steps, all right? But these adjustments mean that there are small electronic energy gaps between chlorophylls. So the energy transfer process is going to have a problem if you wanted to think about it from the point of view of adiabatic theory, all right? And unfortunately, people were basically thinking about it from the point of view of adiabatic theory until we published a paper showing that it was in a very strange non-adiabatic regime in 2013. And so let's go through and just, it's bad because if you look at that pigment I just showed you, and these are results of that paper, you can see that the Born-Oppenheimer potential energy surfaces are right inside each other, all right? They're separated by less than the thermal energy, KT, at room temperature, all right? And so there you have small electronic energy gaps, like I was saying. It gets worse. It turns out that the protein has actually adjusted things so that when you look at the vibrational levels inside those potential energy curves, they're essentially right on top of each other energetically. All right, and that's going to lead to resonance phenomena so that the Born-Oppenheimer picture is completely gone. All right, so what happens when, what actually happens? Well, I mentioned that we did calculations with a non-adiabatic model where we actually worked out using the structural things and spectroscopic things enough about the Hamiltonian to establish those resonances. And then there were signatures of them in two-dimensional experiments of the type done by my group. And what I want to do is give you some idea of how the energy transfer can be so terribly fast that comes out of that model. And so for that, I'm going to use this electronic color wheel, which shows all the possible real superpositions of my donor state B and my acceptor state A. So the color tells you what my electronic character is. Is it A? Is it minus A? Is it B? Is it minus B? Some linear combination. That's telling me by color. And I'm going to use that, look at that color at every position along the exact non-adiabatic eigenfunctions. And so this lowest V equals 0 state, well, it's basically just on the acceptor, right? Nothing to it. This is the vibrational coordinate, the crucial one. But then I go to this next state and it starts off, so it's in a mix of A and B. Then over here, it's on B, and over here, it's on A. So it shouldn't be a surprise to you that you could transfer the energy from A to B within one vibrational period with this kind of non-adiabatic coupling. And that's the basic sort of story of what's happening here. The energy transfer is a little bit slower than that, but that's fast enough to resolve the mystery that we had since Frank and Teller's work. All right, so now, how am I looking at these eigenfunctions? I'm using what's called an exact factorization of the non-adiabatic eigenfunction. And it factors it into an electronic part, which looks kind of Born-Oppenheimer-like, and a vibrational part where I gave it the symbol thorn. And the reason is that the vibrational part, which is a marginal vibrational probability amplitude, just like the Born-Oppenheimer vibrational wave function, is a square root of basically a trace over the electronic coordinates of the vibrational probability density. So I include, all the different electronic coordinates. This is just what's the probability of being there, probability amplitude, and that's why I gave it this symbol that looks kind of like a cutoff feet. All right, and then we have an electronic probability amplitude factor. It's a conditional probability, just like in the Born-Oppenheimer or adiabatic approximation, and it's just obtained by doing this division, and it contains all the sign information, since this is everywhere non-negative. Okay, so that's a weird way of looking at things. These are not necessarily allowed wave functions, and that's why the thorn is there. And in a one-dimensional problem, Hunter showed that non-adiabatically coupled adiabatic basis states are unlikely to have their vibrational nodes at the same position. So the nodes get smoothly filled in. So you're never really dividing by 0 here, and your square root is never crossing over through 0. That was kind of the idea of Hunter's work. And this has been used significantly in work on calculating non-adiabatic dynamics, this factorization. So if we look at that situation before, this color wheel, that's my electronic factor in the exact factorization. And then the amplitude that's shown here is my vibrational factor in the exact factorization. And you'll note that these eigenfunctions don't have any nodes, right? This one comes close to 0 at that point, but there's no nodes in those eigenfunctions. So where do those eigenfunctions come from? They come from a very simple Hamiltonian for a dimer, which just means I have two molecules, an acceptor and a donor. The acceptor has harmonic oscillator vibrations on it. the donor has harmonic oscillator vibrations on it. And then the donor and acceptor in their excited electronic state are coupled. So in the excited electronic state, the energy of the acceptor is a little lower than the average of the two energies. The energy of the acceptor is a little higher. There is a change in vibrational displacement. So the vibrational origin moves a little bit when I electronically excite a molecule, because I reduce the bonding when I do that in general. Not always, but usually. And similarly, same thing happens on molecule B. And then these molecules are so close to each other that there is a coupling that originates from virtual absorption and emission of radiation. Okay, so we have a coupled, non-degenerate homodimer, because they're both chlorophylls, so they're going to be the same. And that's what gives me those states, except before I only showed you one of their vibrational degrees of freedom, and you saw that there were, each molecule is able to vibrate. So now we're going to look at this in the space where each of the molecules can vibrate. And what you see is that what we were looking at before was the anti-correlated vibration, where one molecule is stretching while the other one is contracting, and vice versa. Okay, and so you saw these 5 eigenfunctions before, but now really you can't get rid of any vibrational coordinates. There's also a correlated vibration, and that is adiabatically separable in this model. So, you know, I can just add 1 quantum or 2 quantum of correlated vibration, and everything looks very normal, and I can add 1 quantum of correlated vibration to each of these states. And so that explains the set of states that I show up here. All right, now, we don't really expect that if I put 2 molecules in a protein and then use the protein to adjust their energies, that they will have exactly the same vibrational frequency anymore, right? I mean, if I'm adjusting the bonding in that way, I will have an impact on the vibrational frequencies. So now we'll tweak the model a little bit and allow these frequencies to be different. And that actually happens in the photosynthetic proteins. So they turn out, they tweak them, and the vibrational frequencies are slightly different. In this particular showing, they're exaggerated slightly, but not much. All right, so the equal frequency model. Here are the states being plotted in 2D that you saw before. And now, corresponding states, when the frequencies are slightly unequal. Okay, I can see what happened. My node disappeared there the way I was told that it should. This one is fine. Wait a minute, there are some weird things happening right here. You see little places where the color is just sort of splashing out all over the place. Right? What's going on there? So those 3, it turns out that if you look in a little closer, you can see that these places where color is splashing out are occurring below the very lowest contour of this vibrational factor. And so it's looking like we have sort of point nodes in 2 dimensions, which is more than a little weird. You zoom in closely, and there's the point of 0 amplitude, best you can numerically determine it. And as you go out radially from it, you see that the contours are evenly spaced, right? So what this is looking like is it's looking like we have a point node at the vertex of a right elliptical cone. Okay, so locally, we have a point node at the vertex of a right elliptical cone. Well, how does that happen? What Peter did to figure out how that happened was he plotted the projections of these exact eigenfunctions onto the acceptor and onto the donor. And those are nice and normal. They have nice nodal curves like we would expect in 2D. And where those nodal curves intersect, we get these conical nodes. And then you can do a very simple analysis to prove that these things are elliptical cones locally. All right. And you get 0D point nodes, right, is the sort of picture. Here are the other states, and you can see that exactly the same thing is happening of those three bizarre eigenfunctions that I showed before. And so what's the dimensionality? How does this work? And so if we have an m-dimensional space of vibrational coordinates, then we're expecting m-1 dimensional nodal hypersurfaces in each time we project onto an electronic state. If there are n electronic states involved, nodes will occur at the intersection of all n nodal hypersurfaces. And so the intersection of these n nodal hypersurfaces, that are each m-1 dimensional, occurs at an m-n dimensional surface, unless there's something, requiring by symmetry that some of these surfaces align. All right. This exactly parallels the dimensionality of conical intersections between electronic potential energy surfaces that was first analyzed by von Neumann and Wigner in 1929. And so we called these conical nodes because of that, right? It's not that the node is conical, it's a description of its vicinity, just as it's not that the intersection is conical, its vicinity behaves as a double cone. And conical intersections, you may know, are basically the place where Berry phase was discovered, right? They're degeneracy points, right? So now, what do these nodes look like if you have a conical intersection? So we decided to look at that in a Hamiltonian with the highest sort of symmetry conical intersections possible. And so that meant cylindrical symmetry conical intersection. And so this Hamiltonian looks like the one that we looked at before, except that the vibrational frequencies are exactly equal. The states are exactly degenerate, right? But they are affected in the opposite way by excitation of one vibration. And the coupling is dynamic, not static. It's now a vibration that's causing the coupling. All right. So this is the prototype conical intersection Hamiltonian. And this prototype conical intersection Hamiltonian, when you look at its adiabatic potential surfaces, you see that it has a Berry phase where, as you go around, there's an unavoidable pi phase change or sign discontinuity as you go around the potential surface, looking at the electronic character as you go. The potential surface is continuous, but that sign change in the electronic character causes you to have a half odd integer angular momentum, right? Like occurs with a spin. And this was first discovered by Longet-Higgins back in parts of this in the 50s and early 60s. And then Berry recognized this as an early example of the Berry phase. So what do those eigenfunctions look like? And what do their nodes look like? Here's the 0 point level. You can see nothing too remarkable there. Here's the first pair of excited vibrational levels. And what you can see is you can see quite clearly the half odd integer angular momentum here, right? You've got 3 incipient but not present radial nodes, and they intersect in a node at the origin. And that's an actual node. And that occurs down there as well. This one has kind of a node that's not quite exactly at the origin. This one has 2 spins around the color wheel with a node at the origin. And you can see the sort of 5-fold symmetry from this half odd integer thing there. And then this one's got a couple nodes not at the conical intersection. This has 1 at the conical intersection, 1, 2, 3 surrounding it. All right, so these have a little bit of a strange behavior. And if you look closely at the nodes, you find that there are circular cones at the conical intersection at the origin. And then if you look at some of these higher states, when it takes 2 spins around the color wheel, the radial power law is quadratic. 3 spins around the color wheel, radial power law is cubic. And this suggests that an electronic index might be useful in helping you to connect the radial properties, the nodal properties, and other behavior of these eigenfunctions. And so if we define the electronic index sort of visually without getting into the equations, we can think about it as basically spins around the color wheel. And the reason that we can start using some results from geometry is that except for isolated singular points, the electronic factor forms a differentiable vector field over the vibrational coordinate space. And because of that, you can start sort of getting all the results that lead to Poincaré's theorem for surfaces in 2D to play a role here, just doing integrals around sort of a finite curve in this space. And if you do that, you can start attaching indices to each of these eigenfunctions. Here, there's a net index of 0 because I've got one node with a negative index and one with a positive index. Here, the net index is 2 because I've got one node with a negative index and 3 with a positive index, right? And so the picture is then that the eigenfunction has an index that is, looks to be a useful property, right? Now, that index actually is connected to the index that you would get for the adiabatic potential energy surface in the context of a Berry phase. So if I look at this adiabatic surface over here, I have an index of -0.5, right? Because as I go around it, if I want to go around the color wheel in a counterclockwise fashion, I have to go clockwise around the wheel. And if I want to do it here, it's counterclockwise to go counterclockwise. So I have a positive integer of 1/2 index. And you can see that these two conical intersections flip the indices of every one of these eigenfunctions, right? So there's a connection here between what you might call the sign of the conical intersection and the index of the eigenfunctions that results, right? And the index of the eigenfunctions, that depends on the, a phase choice. And the index here depends on a phase choice, but the relative sign between this and this does not depend on a phase choice. So there's something there that's physically significant. Okay. So we've been getting closer and closer to what the actual photosynthetic apparatus is like as we're going. If you remember, I showed you that molecule and it had a ring, and so we're thinking of a ring we're approximating it as a circle. The next approximation is that it's a square. All right. And so if we look at a conical intersection with fourfold symmetry and what that Hamiltonian is like, it's just like the one we had before. We have our two vibrations, we have our two electronic states, we have our dynamic couplings, but it's a heterodimer's evil twin. The frequencies don't have to be equal, and the displacements don't have to be equal, right? That drive the dynamics, these displacements. Sorry, I lost my subscript formatting there. So what does that do? The adiabatic potential surface now gets sort of distorted out. You'll notice this one is sort of elliptical this way. This one looks sort of elliptical in the other direction. I get two symmetry-related minima separated by two symmetry-related saddle points. And the angular momentum quantum number that I had before is totally destroyed, all right? Because I've blown my rotational symmetry. And so if I start looking at the eigenfunctions as I go from circular to, I'm going to change the displacement for one vibration from circular symmetry here to fourfold symmetric here, jump through a case where it's an accidental adiabatic case, then head towards positive circular symmetry again, you'll notice that even though the nodes are getting split up, the index is behaving nicely and just connects as states cross over from one to the other. So the index seems to be behaving as a good quantum number after I've blown all my angular momentum as a quantum number. What's happening there? The higher order nodes that I mentioned before, so here's one, it's circular if you look really close, but here's a sort of second order node with an index of -2. It splits into two nodes with an index of -1 each as I go away from circular symmetry. All right, and all of those higher order nodes split in exactly the same way into, you know, just the number of nodes with exactly the same sign as their order. The other thing that can happen is the nodes move around as you adjust parameters. The pairs of oppositely signed conical nodes can actually annihilate each other or be created from nothing as you adjust the parameters as well. So it looks like, you know, particles annihilating and creating each other, but this annihilation and creation process preserves the index of the eigenfunction. All right. So now I want to make sort of a last point, and I noticed that my talk is taking exactly 0 time. Right. The last point I want to make is that conical nodes are actually measurable, right? The total vibrational probability density, that's something that you can measure in quantum mechanics. It's an observable. And actually, there have been attempts to measure this vibrational probability density for the deuterium trimer and the hydrogen trimer. And when you look at the experiments that are trying to measure it, they were trying to measure this actually for a case with a threefold symmetry conical intersection. So similar to what I've shown you before. And when they were trying to measure these distributions, what you can see is that some of their measured plots look like they have possibly sort of isolated point zeros in them of the type that you would expect in the probability density for these kinds of conical nodes that I have shown you before. And so it's not clear, you know, you're never going to be able to prove a 0 experimentally, but these are something that you can actually, you know, get closer and closer to measuring. In contrast, at least in molecular quantum mechanics, Berry's phase and conical intersections are features of an approximation. They're actually features of the adiabatic approximation. And as features of the adiabatic approximation, they're not directly measurable. You can look for signatures of the kind of dynamics that they cause, but you don't have any direct way to measure that they're there or not. And so it makes me kind of wonder whether we should be looking for direct signatures of conical, non-adiabatic dynamics by looking for things like conical nodes on the experimental side. So some conclusions here. So these conical nodes are a signature of non-adiabatic dynamics. They don't occur if the dynamics is all confined to a single non-adiabatic potential energy surface. They're stable. They're related to the index that is connected to Berry's phase. They're measurable in principle, and they have a kind of local topological basis where you can show that they, will be stable, right? That the sum of the indices that's enclosed is going to give you the index around the curve. There are a couple of key open questions, right, that I'd just like to highlight. All of the results that I presented today are local, right? I didn't do any kind of global analysis to say what should the index of these eigenfunctions be. But one of the first things that has to be done to try to figure that out is what's the global topology of the vibrational coordinate surface, right? And I just worked in this sort of rectilinear coordinates kind of local topology, and clearly the global topology of a molecule is something a bit more complicated. The other questions are, once you get that global topology figured out, what are the implications of the Poincaré-Hopf theorem? Because that's going to just tell you what the overall index is going to be. And for that, I need some help from Marcus. And we've been talking about that problem a little bit. The other thing that I think is a very open question on the sort of practical side is non-adiabatic dynamics arise from eigenfunctions with conical nodes. And we think we sort of know how conical intersections influence the dynamics, but I think that needs to be kind of reformulated if you want to do things in a more rigorous way, to ask how conical nodes influence the dynamics, the non-adiabatic dynamics that's driving these things like photosynthesis. And so with that, I'd like to conclude by thanking my students, Peter Foster and Bill Peters, Marcus Flaum, for several very stimulating conversations about the overall topology. This work was funded by Air Force and NSF. And then I'd like to thank Marcus for the invitation and all of you for listening. Yeah, so. Stop share.
Maybe stop sharing the screen. And there are questions, either from the inside or outside, external or internal. So, are there questions from your side or from the online audience? Let me ask a question. I mean, you mentioned Langevin-Higgins, and it seems that he kind of was the first who detected the barrier phase. And so it was, if I remember correctly, the date 1975, and Berry's phase was in the mid-80s. So, and I mean, this is not so much known, that in principle, Berry's phase was invented or detected by chemists and not by physicists. So maybe you can elaborate a little bit on this, or?
Yeah, it's an interesting story. Actually, if I think about it, the phase that Langevin-Higgins described is slightly different from the Berry phase. And so if I have a kind of only two electronic states involved, the Langevin-Higgins phase and the Berry phase will be the same. But when I go to more electronic states, I have seen there's an analysis that predates Berry's analysis by Mead and Trular, where what they actually showed that the Berry phase, which they calculated, they stated in their paper that the Berry phase converged to the Langevin-Higgins phase as your distance from the conical intersection went to 0.
Oh, okay.
So it's an even more complicated history than what I said, if I have got the recollections of the timing and the ordering right. And then I believe Barry's paper actually cited Mead and Trular, and it also cited Longet-Higgins, I think. I heard Barry give a talk, and he referred to Hertzberg and Longet-Higgins as some chemists. We thought that was amusing because Hertzberg won the Nobel Prize in chemistry in the early 70s. And so, yeah, it's a very complicated history. I mean, I think what Barry's big contribution was to realize that this adiabatic phase, you know, had a topological basis and would show up in other places. So Longet-Higgins understood there was a topological basis for it, but he didn't really think about all the other applications that Barry did. And so I think that's the thing that Barry should get the most credit for, was showing that it would have all these other applications, right?
More questions? I actually have one more, and that is maybe a comment. And that's you mentioned a couple of times indices. And that's I mean, index theory is a extremely powerful theory within global analysis and non-continuous geometry. And it seems there, I mean, that's my impression at least a bit, that there are various types of index theorems which could be applied here. So there, so one is the index of a vector field, where if you add them up, you get the Euler characteristic that's the Poincaré-Hopf theorem. But there are also other topological invariants leading to indices. I mean, term classes and so on. And it would be definitely fascinating to figure out which kind of index theorems lead or can be applied here, because I think there are various. I mean, definitely Poincaré-Hopf, but I think also other ones.
Yeah, thank you. Yeah, I imagine that there would be a lot of useful ideas that could come from this group about what could be done to, you know, this is very much sort of, this is what we see, this is the result I can use from junior level analytic geometry, you know, junior level differential geometry, and then after that, it looks like it gets pretty deep pretty fast. Right. So.
Okay. From the outside audience, any questions? Okay, then let's thank the speaker again. Or Masoud, did you have a question?
No, I just wanted to thank the speaker. Thank you very much.
Yeah, thank you.
Oh, thank you.
Okay, thank you. And I will announce the next seminar as soon as possible. Thanks. Bye.
Leave the meeting now. Will that be okay?
Let me just.